On the other extreme, so bound resource is sort of one extreme of asymptotic distillability. The other is perfectly reversible states. And these are states where the rate of formation and the rate of distillation are equal. So for the quantum case, we know that pure states have this, but there's actually a more general class of reversible states, so-called flagged pure states. And these are just mixtures of pure states where Alice and Bob can determine which state they hold in that mixture using LOCC. And also, Minshu and I have done some work on studying the classical analog of this, and we've identified a class of distributions that have a classical flagged structure. But it's still open whether or not these are the entirety of the reversible class of states that have reversibility. OK, so what I want to do in this talk is actually add to another common feature to these two resource theories. And this is the question of round complexity. And the basic question is, how does increased rounds of interactive classical or public communication enhance the ability to process quantum or secret information? OK, so just to discuss some previous work done and actually to draw some continuity to QIP of last year, this was a talk by Braverman et al. Where they considered the communication complexity for the disjointness problem. And their result is identifying a trade-off between the number of rounds that you're allowing of interaction and the amount of communication you actually have to perform. And this is similar to some previous work done where a type of problem is studied where in R-1 rounds for a given problem, you need a certain amount of communication. But if you were allowed one more round, you're allowed, you can achieve the problem with substantially less communication. But one thing to note here is that the type of communication we're talking about here is quantum communication. So this is sort of outside of the LOCC, LOPC framework, because again, we're interested in the classical communication complexity. OK, so some more previous results in this area where we're talking about LOCC round separation. Probably early on, the BDSW paper, where they look at entanglement distillation. They give a nice example of states that are distillable using two-way LOCC, but are not distillable using one-way LOCC. And I point to this paper or this poster that was given on Monday or Tuesday by Levitsky and Dada and Smith, where they obtained some more results on one-way distillability. And you can see some examples of this. So that's for entanglement distillation. For LOCC state discrimination, there's a number of papers on this where there's a gap between two-way LOCC and one-way communication. In particular, this paper shows a separation between R round LOCC and R-1. So in this paper, Shin and Duan construct an ensemble of states where if you're allowed R rounds of LOCC, you can perfectly distinguish the elements of that ensemble. But with fewer rounds, you're unable to. And for another task, if you are interested in multipartite systems, so this would consider three parties and you want to perform a LOCC state transformation, there's been some work that separates unbounded LOCC from finite round LOCC. So I kind of want to pick up with this last task here of state transformation. And I want to draw your attention to an example that fails to separate the rounds. So here the task is Alice and Bob have some initial pure state. And they convert it into a mixed state, sigma. And they do this in R rounds. Well, it turns out that you can always convert this R round protocol into a one round protocol that achieves the same transformation. And so this was first proven by Lowe and Popescu in 2001. And so the message is that for a pure state initial to a mixed state final, one round suffices. And one thing I want to emphasize about this result is that the round compression holds for arbitrary dimensions. Okay, so it doesn't matter what your input or output dimensions are. You can always get this nice one round compression. And actually, this result is absolutely crucial to proving the majorization condition for convertibility of pure states that we're familiar with. Because otherwise, if you weren't able to reduce it down to one round, it would become much more complicated. OK, so this is the result. And then I think a very natural question then is whether the same thing holds for an initial mixed state. So if you have a mixed state row, do you also get a round compression? Can you perform this in using just one round of LOCC? OK, so our result then is no, you can't. Specifically, for every R, there exists a state transformation rho to phi that needs R rounds of LOCC to achieve. So what I'll do for the next 10 minutes or so is kind of go over the construction of this and the proof of how this works. So the states are constructed in 3 steps. And the first is we define a probability distribution. It's a tripartite distribution. We call it B1. And it's easy to understand this distribution if we just draw a picture. So the way to understand this is this grid here. We have y, so this is Bob's variable on vertically, x variable horizontally. And inside the grid, those values are Eve's variable. And these are 8 equiprobable events. So for instance, if we just look at this point here in the grid, this is the event that Alice holds 2, Bob holds y, and Eve holds 1. And because these are equal probable, there's 8 total events. So the probability of this event is 1/8. OK, so this is how we're going to represent our distributions. Now, this distribution has some very nice properties. And the first is that if you're given z, then Alice and Bob have 1 bit of perfectly shared randomness. So for any value of z, so for instance 3, you can see that Alice and Bob have perfect shared randomness there. So this should get Alice and Bob very excited, because if they can determine z using public communication without leaking any information to Eve, then they will have exactly 1 bit of secret correlations. And so actually, there's a protocol that does this, and maybe you can see it right away. But it goes as follows. So Bob announces whether his variable belongs to the set 0, 1, or 2, 3. And this has you can depict it like this. So it either belongs to this red block or this green block. Now, of course, Eve learns nothing about this communication, right? Because she already knows, just looking at her variable, she knows whether she belongs to green or red. So she learns nothing about it. However, Alice learns quite a bit. In fact, Alice learns exactly the value of y, because within each block, if you're given x, you can determine y exactly. OK, so this is how Alice and Bob can obtain key just with this. But remember, our goal is to build a quantum state. So the way that we do this is we now take our distribution and we embed it into a tripartite state. So we introduce a tripartite pure states where the probability amplitudes are given by this distribution here. And then what we do is we trace out Eve. And what we end up having is a mixed state here. And each psi z in this mixture is maximally entangled. So using the classical protocol that I described on the previous slide, we can turn this into a one-way LOCC protocol as follows. So in the first round, Bob projects in the 0, 1 subspace or the 2, 3 subspace. He communicates that to Alice. And then given that outcome, Alice knows where to project, right? So if it's in the 0, 1 subspace, Alice either projects it in the 0, 1 or the 2, 3. On the other hand, if Bob projects in the 2, 3, then Alice has to choose a different projector. But the point is that each of these branches, they obtain a maximally entangled state. So with a one-way protocol, we're able to distill this mixed state into an EPR state perfectly. OK, so this was just for one way. Now what we'll do is we reiterate this. So we use this as our basic building block, and we build up. So here we went from B1 to B2. So what we do is we take a copy of this, and we do a permutation. So we permute the rows here. And at each level, we add Eve's alphabet size is doubled, and also one of the parties is doubled. So you can see from B1, we made a copy. We doubled Eve's variables. Then to get from B2 to B3, we just take this, make a copy of it. And you have B2 and B2 bar. And then to get B4, you take B3, you make a copy of it, et cetera. And actually, so this looks extremely complicated, but it has a tremendous amount of structure. Because what we're doing at each level of this is we're copying the structure from the previous round and just shifting things into a disjoint set is a way to think about it. And so we've called these origami distributions because it has this structure that you are kind of folding the distributions to build up. OK, so then the quantum state is obtained in the same way that we embed these distributions into a tripartite state, and then we trace out Eve. You can obtain in R rounds of LOCC, you can attain a maximally entangled state just by undoing this folding process. So the protocol is exactly similar to the one-round protocol, except now we've just carried it out for R rounds. So it's not too hard to see that R rounds of LOCC suffice to do this transformation. But the major question is, what about if you have fewer than R rounds? Can you still perform this transformation? And the answer to this is no. This is sort of our result. And to prove this, I can just describe it. The key observation is the following: that this first point holds in general for any mixed transformation to a pure state. If you want to do this perfectly, you have to transform every state in the mixture to your target state. Okay, so that's the first thing that we need, is we have to transform each of the psi z's into phi in this protocol. The next observation is that because each of these psi z's are maximally entangled, they have a Schmidt rank of 2. Okay, and the Schmidt rank itself is an SLOCC monotone. So the SLOCC is stochastic LOCC. And so what that means is that if at any point in the protocol the Schmidt rank drops, it can never be increased again with any non-zero probability. And this has a very strong consequence, because we know that each of these must be converted into maximally entangled states. So at each round of the measurements, the psi z must either be eliminated or its Schmidt rank remains the same. It can't decrease down to 1, because once you have 1, you can't convert it into an entangled state. And actually, this is the essential ingredient in the proof, that just this observation that at each round, psi z must be eliminated or Schmidt rank remains the same. And it actually forces Alice and Bob to perform the correct measurement sequences. To give you a flavor of why this is so, let's consider an example. So here's the distribution B3. OK, now let's suppose that Alice is going to be the measuring party. And suppose she wants to eliminate psi 1. OK, so that's this guy here in the way we've sort of drawn these distributions. So what will she have to do to eliminate this? Well, she's going to have to eliminate her local subspace spanned by 2 and 3. That's the only way she can eliminate that state. However, if such an outcome were to occur, that she projects into the orthogonal complement of this guy so that 2, 3 is eliminated, what's happened is that you've decreased the rank of these other states: psi 2, psi 3, psi 14, psi 11, psi 3, psi 9. So a way to think about that is there's no entanglement left in these states on the post-measurement state after Alice makes that measurement. OK, so but this, of course, is not allowed because of this constraint. So the only way that she could avoid this is actually if she were to eliminate all of these states. But doing so would cause her to eliminate everything. And this is not possible. So the conclusion here is that Alice cannot eliminate any states in the mixture if she were to measure in this particular distribution here. OK, so how would this be avoided? Well, so Alice can't do anything, so we have to throw it back to Bob. And there is something Bob can do here. Bob can just measure in the 0, 1, 2, 3 subspace, or the 4, 5, 6, 7 subspace. So when he makes this, so he either projects here or here. And you see that we haven't destroyed any of the Schmidt ranks in this measurement here. So this is still an allowed thing. But what have we done? You see, we've taken our B3, and what remains is something that's equivalent to B2. So it's up to an SLOCC transformation. It's essentially B2. So this constraint has forced Bob to play fairly how we want him to play. It's forced him to make the proper unfolding to go from B3 to B2. OK, so this is just the example. You can imagine now doing this for R rounds. And so if we started off with row R, at the end of R minus 1 rounds, we would go from row BR down to row B1, and something that's up to an equivalence, SLOCC equivalence. But it's not difficult to show that if you have this and you're allowed no further communication, you cannot turn this into a maximally entangled state, pure state. So if R minus 1 rounds you're unable to do it, then you do need R rounds to make this transformation. Again, the idea is it's just sort of showing that if you have fewer than R rounds, you end up in a situation where you can't obtain a maximally entangled state. OK, so that's sort of the rough idea of the proof for the for the quantum problem. But now I want to consider the analogous classical problem. OK, so here, the goal for Alice and Bob is, now thinking classically, is they want to obtain secret key. So we want to have a similar sort of lower bound on the amount of communication they must do. So the question is, how many rounds of LOPC does it take Alice and Bob to make this transformation? So in the quantum case, the proof relies crucially on the Schmidt rank and the fact that it's a stochastic monotone. So the question is, what is the classical analog of Schmidt rank? And if we can somehow define something or find an object that behaves similar to the quantum Schmidt rank, then we will be able to quickly answer this question. OK, so this is a quantity that we call the secrecy rank. And to kind of motivate it a bit, let's go back to the Schmidt decomposition of a bipartite pure state. So one way you can think about the Schmidt rank of this state is it's the minimum number of product states whose span contains phi. Right? You can't express phi as a linear combination of any fewer product states than it's Schmidt rank. So now suppose that Alice and Bob measure their state phi in the Schmidt basis. So they'll generate some distribution that has this form here. So these are the delta functions. And so it's Alice and Bob have perfectly correlated outputs, and with some distribution PW, which was just the Schmidt coefficients there. OK, but one way you can think about this particular distribution is it has this structure, that there exists some auxiliary variable W, such that x and y are independent given W. Now, in this case, it's somewhat trivial because W is equal to x and y, so this Markov chain holds trivially. But nevertheless, it's one type of distribution that has this property. And this is what we identify as being sort of the defining property of the secrecy rank. So we propose this definition. First, consider an uncorrelated distribution where Eve is out of the picture. So we want to minimize over all auxiliary variables that render x and y independence. And this is just the range of W. OK, so it's the number of events where W has non-zero probability. OK, so this is fine. This is how we define for an uncorrelated Eve. But what about for a correlated Eve? All right, so now, again, we're going to go back to the quantum scenario. And we're to seek for some sort of intuition on how to define this. And recall the definition of a Schmidt rank for a bipartite mixed state now. So this is proposed by Terhul and Herdecki. And the way to think about this is, for a mixed state, you look at all possible ensembles that realize, pure state ensembles that realize the mixture. And in each of the ensembles, you compute the Schmidt rank you compute the maximum Schmidt rank among all the states in the ensemble. OK, so with this definition in mind, let's go to the tripartite distribution. And we can think of a distribution Pxyz as defining an ensemble of bipartite distributions, right? So for every z, we get another bipartite distribution Pxyz. So with this in mind, we propose the following definition of a secrecy rank that it has the same structure that we look at the secrecy rank of the bipartite distribution maximized over all z. You see, unlike in the quantum case, we don't have this freedom of we don't have to do a minimization over ensembles, because classically there is only one ensemble for your distribution. So we don't have this minimization here. OK, so there's another form of it. OK, so we've now established this correspondence between secrecy rank and Schmidt rank. And the main property is that the secrecy rank is an SLOPC monotone. So just like Schmidt rank is a SLOCC monotone, secrecy rank is a stochastic LOPC monotone. And what that means is that for any sequences of messages in your protocol, you cannot the secrecy rank is monotonically decreasing. So with this quantity established, the quantum proof translates literally verbatim into the classical setting, and we're able to derive a lower bound on the transformation of a tripartite distribution into a secret key. So if we start off with BR, you need R rounds of LOPC to do that. OK, So just to get to some conclusions here, so here's our main result is that we have this analogous structural result between the quantum LOCC and classical LOPC. And actually, we're able to give us somewhat of a slight strengthening. So for any r, there exists some non-zero epsilon that you can get that you are unable to get with an epsilon close to your target states in fewer than r rounds. And this follows just from a compactness of LOCC and compactness of LOPC. And also, we can generalize in another way. So since everything is based on this notion of ranks, we can consider partially entangled states and weakly correlated secret key. And we're able to show this, that for every r and any lambda between 0 and 1/2, this transformation also requires r rounds of LOCC and LOPC. Now, what's interesting is somewhat interesting maybe, if you take lambda to be 0, of course, what happens? So when lambda is 0, you have no entanglement here, and you have no shared correlations there. So of course, you can do that in 0 rounds. These are free states in your resource theory. So you have this discontinuity in round number. So as lambda approaches 0, you need r rounds to do this transformation. But when lambda is equal to 0, you can do it in 0 rounds. OK, so I'll just end with some open questions and future work. So first of all, just some main drawbacks of our approach is that the dimension scales poorly. You have 2 to the r in the size here. So the natural question is, can we find examples with bounded dimension? And I said this with some slight strengthening that we have restriction on how close you can get. You can't get with an epsilon. But at the moment, we have no way to actually lower bound this epsilon, except just saying that there exists some non-zero epsilon. Another interesting question is for asymptotic transformations. OK, so here we have n copies, and we want to go to m copies, and we want to know what rates are achievable. So we can ask, what is the r-round asymptotic distillation of both our mixed state and our distribution? And maybe an intriguing question is, if we consider asymptotically, do we get some sort of round compression? Right? So maybe you can distill at a rate, you can distill one key or of 1 bit of key or 1 e bit in fewer than r rounds. And a final note is that these states that we've created, actually the entanglement cost and the distillable entanglement are equal. And actually, this is what sort of motivated us to construct these distributions, because we were studying this reversibility problem. And what this says is that asymptotic entanglement reversibility may require r-round protocols to actually distill at optimal rates. And thus, the states with reversible entanglement can have very complex structure. So this is some additional work that will be done. And with that, thank you very much.
Questions, Todd? Do we have people with microphones? All right.
Wow. Earning your keep, Mark.
You're going to make you fit this way. Yeah. So can you construct? So I'm interested. You could go to an asymptotic limit in a different sense in the number of rounds, right? So could you construct an example where you want to transform a rho to a sigma, and you can't do so exactly in any finite number of rounds, but you can approximate it better and better with more and more rounds?
Yes. So, well, for bipartite systems, yeah, actually, so we have examples of this for both tripartite pure states and for bipartite states as well, where exactly what you said, you need, as you allow more and more rounds, you can get closer and closer, but in the limit you can do it, but for any finite you cannot obtain it. Yes.
Any other questions? So I'm wondering if you have further applications of this quantity that you called secrecy rank?
Oh, that's a great question. Yeah, so this quantity here. Let's see, where was it? So this something similar to this appears in an older paper in the classical literature by Weiner, and when he introduces something known as the common information for two variables, and what Weiner does is he considers a similar minimization over all auxiliary variables that leave x and y independent, but the quantity that you're minimizing over is the mutual information between x, y, and w. Okay, so it's similar in flavor to that in that we're interested in this variable w, but instead of measuring the mutual information, we just want to know the range of it. But you could consider, and this is something to answer your question that I'm interested in, is studying all different types of entropic quantities on that side and understanding W in different settings as well.
So you could put other quantities in there, like besides rank and mutual information?
Sure, like you could look at the entropy of W, and that would give you something. And I'm almost positive that would also be a monotone. So it would give you a secrecy monotone as well. Any sort of Rainey entropy.
Like what properties would you need for the resulting quantity to be a monotone? There you have rank, and you mentioned mutual information. What property would you need for that quantity in there for it to be a secrecy monotone? Do you know?
Yeah, so this is just my intuition here, but this W, the way I think of this W is somehow being similar to the Schmidt coefficients in a bipartite state. And so just as we can define entanglement monotones as functions of our Schmidt coefficients, I feel confident that this W will also have it. So this goes back to some of the work by Giffrey Vidal, where he just characterizes general entanglement monotones based on the Schmidt coefficients using certain properties. So I think something similar can be done with this W.
Okay.
Yeah.
Oh.
Yeah.
Thank you. So this is just to clarify. So do we know, like, if we put a bound on the dimension, can it still be that we need more and more rounds?
For tripartite systems, yes, that is true. We do have examples of that, but for examples like this, a bipartite mixed to pure transformations, don't know.
And what do you suspect?
Yeah, I suspect that you could find something like this. Yeah.
Okay, let's thank Eric again.
Thank you.